Alright, so today's video may be a little bit long since I will just solve multiple similar binary search questions in this one video. So the first question here is 162 find peak element. So basically we are given an array of integers and it's not sorted, and we are asked to find the peak in the array, just any one of the peaks. A peak is defined that it should be strictly larger than the element on its left hand side and the elements on its right hand side. And we consider like nums -1 and nums n. N is the length of the array to be like the smallest ever value, just -infinity. So let's see, for instance, if we have an array that is only 1 and 2, then actually 2 can be considered as a peak, since note that the element after the last element in the array, if we just imagine there's any element after the last one, that this 2, the one after 2 should be -infinity, so 2 is definitely larger than that 1, so actually 2 is a peak. And if we just and similarly, if we are given an array that is 2 and 1, then 2 is also a peak, since the position before the strictly the first element in the array is considered as -infinity, so 2 is definitely larger than that. And since 2 is also larger than 1, which is on its right hand side, then 2 is considered as a peak. Okay, and this question also asks us to solve this problem in log n time. So actually this log n just reminds me of binary search, so I will just start by doing binary search. So actually the logic for binary search is very basic, it's very simple. I don't want to repeat that again. And just first, let's just put a case here and to analyze the question. So first things first, I think we have to rule out all the cases where the array is just too small. Its size is too small. For instance, there's only one element in the array, that's definitely the peak. If there's 2 elements in the array, we do not need to go into the binary search actually, since we can just compare the 2 elements and the larger one should be the peak, right? So our algorithm, I think we should just mainly focus on the cases when array length is equal to or larger than 3. And for instance, here's a simple case, and we can see that 4 is a peak, 3 is a peak, and what if we just add an element here, right? We just add one element here to make the case easier, since then there's odd numbers. And firstly, we want to start the left at this point, and we start the right at this point, right? And then the mid should be this one. And then let's see, like we have to compare this one with the 2 adjacent elements, and we find out that 1 is larger than this 0, but 1 is smaller than this 3. What does this tell us? This tells us that this element 1 cannot be the peak, also this 0 cannot be the peak, but this 3 possibly it can be the peak. So we just move the left to mid +1. We just move the left to this position. And similarly, if we just change the position of this 3 and this 0, then we can know that 1 is not gonna be the peak, 0 is not gonna be the peak, but this 3 possibly have the potential to be the peak. So we just simply move our right to this position, right? And also in another case, if we find out that 1, let's see, if 1 is larger than both elements next to it, 1 is larger than this 0, 1 is larger than this 0, then we can just directly return this one, since this one is clearly the peak. And in another case, if one is smaller than both of the elements, then well, then we can either just move our right to the element on the left hand side, or we can just move the left to the right elements at the right hand side. And I know, by doing so, we're kind of discarding one element that has the potential to be the pick. For instance, if we move this right to this element, then we're actually discarding this element. We're just putting out of our future searching range, right? Since in the next iteration we will only be searching in this range. But we do not need to worry about this case, since there may be multiple picks in the array, and we only want to find just one array. And by doing so, we can ensure that although we may have missed some picks, but there will exist just at least one pick in our searching range in the next iteration right here. There must be one pick. Why? Since for this element, let's see, like for instance, there's 3 elements, and which is the minimum number of elements that are needed to start our comparison. Since if otherwise we end up with the corner case that there's only one element or there's only 2 elements in our searching range, then we'll just directly go out of the while loop and just do the the easiest comparison to decide which is the pick, as we said before in the start of the video, in start of the analysis. And here we can see that in this case 4 is the pick, right? But what if what if 4 is not the pick? How can we make 4? How we can just make that 4 is not the pick? The only way to do so is that we let this position, the first element, is larger than 4, right? Then in this case, this only element will be the pick, right? So there's still a pick. We can still find it. And in another case, what if like 4 is smaller than this 3? And if we look at the question again, we imagine that is strictly greater than outside the boundary, right? So okay, so what if like this element is smaller than this 3? Then that's just obvious, the 3 is gonna be the pick, right? So by doing so, we just ruled out all the possibilities, and we all see that even though we have discarded maybe some possible picks, we will still have a pick in our searching range. Okay, so this logic seems workable. Then we can just directly go to the coding part, though we still need to pay attention to the details. So for instance, if nums.length is smaller than 2, then we just directly return 0. Note here in this question it asks us to return the index of any picks, so we just return 0. Since there's only one element in the array, then it must be the pick, right? Then we just, this is just obvious, so we just initialize the 2 pointers for the binary search, nums.length, right? Nums.length -1, sorry. And then since at least we need 3 elements in our searching range, so left must be smaller than right -1. And then we calculate the mid equals to left plus right minus left divided by 2. Note here we're calculating this way instead of using this way, like mid equals to right plus left divided by 2, since this way of doing the of finding the mid may result in integer overflow if the right is very large and the left is large too, then we may get overflow. Okay. So and then so the most obvious case is that nums mid is larger than nums mid is larger than nums mid -1, and also nums mid is larger than nums mid plus 1, then I can just directly return mid, since this obviously tells us it's the pick. And then in other case, so else if nums mid is actually smaller than nums mid plus 1, right? So in this case, we know that nums cannot be the pick, but nums mid cannot be the pick, but nums mid plus 1 may be the pick. So we just put our right pointer here, and else if nums mid is smaller than nums mid minus 1, then we just move our right pointer. And why I'm always using else if instead of if else if else is because that I want to write down all the conditional statement clearly, and it's much easier for future debugging. Okay, so it seems like we're good with this loop, and then we need to handle the end case. So now imagine that we are already out of the loop, which means that we only have 2 elements left in our searching range, and actually just at most 2. Actually we can have 1. Right, since somehow maybe sometimes like the left may be equal to the right also, and know that these 2 elements or 1 element can be the first one in the array or last one in the array. So we need to be very careful about index sort of boundary problem. So let's see that first we need to rule out all the possibilities of index sort of boundary. So if nums left is equal to 0, then we just simply need to compare like nums left things. If nums left is equal to 0, then it's just automatically larger than the one just that imaginated elements on its left hand side, since it's negative infinity. Then we only need to compare it with the element on its right hand side. Right, if it's larger than elements on its right hand side, then we just return left. Right, and else if nums left is not larger than, is not equal to 0, if nums left is not larger than 0, then we also need to be sure whether, like, just in case, in some cases, I do not want to give specific examples, since now I just don't have much brain to think about it, but maybe in some cases the left pointer may be pointing to the last element in the array, since we are doing mid plus 1 operation here. So let's see, like if nums left is equal to nums the length minus 1, then we just compare it with the elements on its left hand side, left minus 1, then we just return left, since the left is gonna be the pick. And else if both is left hand side and right hand side is within the boundary, there's no index out of boundary arrow, then we can just directly compare, like if nums left is larger than nums left plus 1 and nums left is larger than nums left minus 1, then we return left. And note that we are not using like right in this comparison, since I know somebody may think that obviously like the nums left plus 1 is just the nums right, but actually sometimes left may be equal to right, so it's not correct to do so. So we just do it in the most fundamental way to avoid any possibilities of errors, right? And also the same logic just repeats for nums right. Nums right, if right, since right, so we're just doing the same logic here. And actually, based on our previous deduction, if we only get 2 elements left, just the right and the left, then one of them must be the pick. Right, since otherwise, if none of them is the pick, then we must have found the pick in the previous iterations in the while loop. All right, so let's run the test cases to see if there's any bugs in it. Well, it seems like nums.length minus 1 well, start off illegal, start off the else if, sorry. Else if. Oh, here. Else if, yeah. Else if. That's so silly. That's so silly. Missing return. Oh, yeah. We're missing return statement. So actually, we will get return statement for sure. Speaking about the logic, but the compiler needs a return statement, so we just put -1, and it's just easier for us to debug. Wait, we still got an index out of boundary problem. Why? So let me see. Oh, sorry, my bad. Here we should only be just we should only be checking the index instead of like the element in the array. So right, here's a logic arrow, and that's right. Okay, so I think now we will be fine. Right, okay, so let's submit. Right, so we get kind of the perfect answer. And let's analyze the time complexity. So here is just O1, and in this loop it's just a binary search operation, so it's O log n. And finally, this AND case operation just those if else statement to check the final 2 elements left in our searching range is just O1. And since O1 is negligible compared to O log n, so the final the time complexity of the algorithm is O log n. Okay, so we're basically done with this problem, and let's start do the next one, 153. And okay, so considering the length of this video, I will just put that problem in another video. All right, so see you soon.